So 12.2a will be about these special types of sequences called arithmetic. Now, as discussed in 12.1, when it comes to figuring out the equation, figuring out the pattern or the structure of any sequences, that is typically a difficult question because there's nothing to solve for. There's no formulas. You just have to go on gut instinct, experience, intuition, and recognizing patterns. But some patterns are easier to recognize than others, and because some certain patterns are easier to recognize than others, they're easy to study, and mathematicians give names to these easy to understand structures. Perhaps one of the simplest ways to generate a sequence is through constant addition. And we've seen that before, right? You don't have to write this down, but 2, and then let's constantly add 3, 5, 8, 11, 14. That's an easy pattern to create, and therefore should be easy to describe. Start with 7, and heck, we can subtract. Let's constantly subtract 2. 5, 3, 1, negative 3, so on and so forth. So because that is a pretty easy way to make a sequence, just start adding or subtracting the same amount over and over and over again, it was a very natural question to mathematicians. Do they have a predictable structure? And of course, since we gave it a name, the answer is probably yes. Let's go ahead and see what that structure is. So let's go ahead and build these predictable sequences, right? We'll start with a number, and then we'll constantly add an amount to it over and over and over again. Since we want to generalize or sort of make a formula, let's use symbols. So suppose we had, we had a starting number. Let's call it a sub 1 for the first term. And we wanted to generate a sequence by constantly adding or subtracting in the case of negative numbers, constantly adding a common number. Let's call it D for that number. So let's build this sequence. So we'll start with the first number, a sub 1. Right, there's our first term. Now the idea is to get to the next number, we're going to just add the same thing over and over again. So in this case, we're going to add the number D. So that should give us a plus 1D. Then to get to the next number, we're just going to do the same thing. We're just going to add D. That's a plus 1, a sub 1 plus, well, D plus D is 2D. And then to get to the next number, we're going to add another. That's a sub 1 plus 3D. And then hopefully I don't have to write it anymore, but you guys are picking up the pattern. The next number should be a sub 1 plus 4D. The next number should be a sub 1 plus 5D, so on and so forth. So there we have it. This generalizes every single sequence in the whole universe that follows this easy to recognize pattern, starting with a number, and then you're just constantly adding something over and over and over again. Well, can we come up with a formula? That's the question. So what is the nth term of the sequence? Well, it's all about looking for patterns. So hopefully everyone can agree that in every single term, there's that starting number that we had, a sub 1. So that's pretty easy to recognize. That's constant throughout. Now we do recognize that, with the exception of the very first term, every single term has some sort of multiples of the letter D. Let's go ahead and put the term number above these expressions. Maybe you'll see it more clearly. So the very first term is the first, n sub 1. This relates to n sub 2, the third n equals 4, n equals 5, n equals 6, so on and so forth. So with the exception of the very first guy, every single other term has a multiple of D added to it. Now the second term only has a single D added to it. The third term has 2d. Fourth term, 3d. Fifth term, 4d's. Sixth terms, 5d's. Hopefully it's very obvious to everyone that the amount of d's you're adding will be exactly one less than your term number, one less than n. So it should be n minus 1, that's one less than n, number of d's you're going to add. And it actually works for the very first term as well, right? Because 1 less than 1 is 0, so you're adding 0 d's, which is exactly what's going on here. So there we have it. We have the structure. We have the equation for every single pattern that behaves in this manner, starting with a number and then constantly adding the same number over and over and over again. Patterns that exhibit that behavior. Patterns that are just constantly adding or subtracting in the case of negatives are called arithmetic. So this is the definition of an arithmetic sequence. An arithmetic sequence is a sequence where there exists a constant common difference, and the letter we use for difference is d, where there exists a constant common difference d between any two consecutive terms. In other words, that sequence that we generated. So you start with the first number, then you add another d, then you add another d, then you add another d, so on and so forth. The nth term of an arithmetic sequence may be found. I'm always paranoid and hit record. Okay. May be found by a sub n equals a sub 1 plus n minus 1 d. Where a sub 1 is the first term, d is the common difference. Now it is the number that you're constantly adding, or if it happens to be negative, subtracting. It's the number that you're constantly adding as you progress through the sequence. So you have to go in one direction. Note, d is any two consecutive terms, but you take the latter term and you subtract the former terms. For instance, you don't have to write this down, I'm going to erase it later. If you had a sequence like 2, 5, 8, 11, 14, to figure out the common difference, you just pick any two numbers, say here, and it's always the later number minus the earlier number. So in this case, we know that d is 3 because 11 minus 8 is 3. So in the case of subtraction, say, negative 2, negative 7, negative 12, negative 17, so on and so forth. Take any two numbers that are next to each other. It's always the later number minus the earlier number that gives you the common difference. So that's sort of the key thing here, that sequences, the domain are natural numbers, it goes in one direction. The natural numbers must increase. So to figure out what the separation is, the common difference, it's always the later number minus the earlier number. But this is sort of like the important thing here. That's wonderful for us, because before, when these sequences, their explicit formulas were all mystery and experience, and you just have to see the tricks. When it comes to arithmetic, if you recognize these patterns here, there is a formula that you can always run to plug in and get an equation. So for example here, suppose I ask you to find the nth term, or let's say find the first 6 terms and the nth term and the 300th term of 13, 7, 1, -5, so on and so forth. Now this would seem like a lot. Man, this is very difficult. How am I supposed to do this? Well, you first need to recognize, is there a pattern? Now, they're all odd numbers, they're positive and negatives, there's no alternating. This seems like a very difficult question, but the first thing I always look for when it comes to figuring out sequences is there a common addition, subtraction, or is there common multiplication or division? In this case, hopefully it's not very hard to see that there is a common subtraction, right? Remember, you pick any two numbers. Well, let's just go in order. And then you subtract them, but it's always the later minus the former. So it's 7 minus 13. Basically, what would you have to do to start at 13 and end at 7? Well, that's, hopefully you guys know arithmetic, that is subtracting 6, -6. And you should recognize that that is going to be the same pattern over and over and over again. So all of this work tells me that my common difference is -6. And we can just see, right, there's no guesswork, that the first term is 13. So because there is a common difference, I know for a fact that this is arithmetic. So that's the key here. I guess I should scroll up and mention that. This formula, I mean, it's sort of obvious, but I'll state the obvious. This formula only works if you have an arithmetic sequence. And by definition, an arithmetic sequence is a sequence where you are constantly adding or constantly subtracting throughout the terms. So in this case, since there is common subtraction, my common difference is -6, I can read that the first term is 13. Therefore, let's answer this out of order. We immediately know what the nth term is. A sub n, the nth term, is a sub 1 plus n minus 1 times d. Now, different people are different, again, to speak the obvious. Different classes, different teachers have different expectations. When it comes to arithmetic sequences, I actually don't simplify, because this tells me a lot of information. It clearly tells me what the common difference is. It clearly tells me what the first term is. So I actually just like to leave my answer like this. But, if you're checking your answer in a worksheet or in the answer key and it doesn't match, 9 out of 10 times what they did was they simplified it. So I just want to reiterate, this is fine for me. But you might also see a simplification. So what is that? They distribute the -6. So that is a -6n plus 6. So you might see something like 19 minus 6n. They're the same answer. So, just make sure, pick your poison. As long as it's mathematically correct, I am fine. So we found the nth term. We need to find the first 6 terms. Well, 1, 2, 3, 4. It's nice. They already gave us the first 4 terms. So a sub 1 is 13. A sub 2 is 7. A sub 3 is 1. A sub 4 is -5. Now, we actually don't need the formula because we know what the pattern is. Just keep subtracting 6. So instead of plugging and chugging, just keep subtracting 6. A sub 5, you subtract 6, that's a -11. A sub 6, you subtract 6, that's a -17. But the last part of the question says find the 300th term. I'm not going to be subtracting 6 294 times. So this is when I would actually use the formula. So a sub 300 is just plug and chug. 13 plus 300 minus 1 times -6. You either use pretty impressive mental math or use a calculator. That's going to be -1781. So there we have it. There is the first term. Let's group these together because there were one answer. There's the first 6 terms. Here was the nth term up here, and here is the 300th term. Easy peasy, right? So, if you know it's arithmetic, that's the key there. If you know that your sequence is arithmetic, it should be an easy problem, because that means this formula is unlocked. That means everything can be described by that formula. Alright, let's take a look at this next example here. I want to do this next example to showcase that although we do have formulas, we don't have to be reliant. You can, but we don't have to be reliant with it. Let's take a look at this guy here. Suppose they told you that the 11th term of an arithmetic sequence is 52. And the 19th term is 92. Find the 1000th term. So usually, if you were to erase all the information, and if you usually saw something like this, I mean, that usually means, hey, I need a formula so I can plug stuff in. That makes my life simple, right? 1000th term, that's really, really big. I don't want to constantly count to 1000. Let's use a formula. Let's go ahead and parse the information that they gave us. So they told us at the very beginning, it's arithmetic. That's key there. They told us the 11th term is 52. I'm going to write that symbolically. So what they just told me was a sub 11 is 52. They also told us that the 19th term is 92. A sub 19 is 92. Now, we could do this the traditional way, which involves creating a system of equations, so on and so forth. But we don't have to do that because we know it's arithmetic. We know it has a predictable behavior, predictable pattern. So if you can imagine the entire arithmetic sequence laid out. Here's the first number, the second number, the third number, the fourth number, the fifth number, so on and so forth. I'm not going to write all those dashes, but if you imagine the entire sequence, we don't know what it is, but pretend we do. Imagine the entire sequence laid out. Right, and let's call this the 11th term, comma, dot, 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 and let's call this the 19th term. Well, according to the problem, we do know what those numbers are. We do know that this number is 52. We do know that this is 92. Now, you're probably thinking, well, that still doesn't help us because we don't know anything about this arithmetic sequence. Remember, the formula, if you're going back to the formula, we need to know what the first number is. We need to know what the common difference is. Well, that is true. Arithmetic sequence is defined by a common difference in the first term, but the ultimate conceptual idea of arithmetic, repeated addition. So I know that in between the 11th term and the 19th term, I'm adding a common difference d. I'm adding a common difference d. I'm adding a common difference d, so on and so forth. So here's my question that pops into my mind. How many times are we adding d between the 11th and 19th term? In other words, how many d's are there between the 11th and 19th term? That, I think, is a simpler question. That's a counting question, right? You have the 11th number, you have the 19th number. In between them, how many d's are there? That should be a simple subtraction problem. 19 minus 11 equals 8 d's. So what? Well, since this is arithmetic, we know if we start at 52 and add 8 d's, what number should we end up with? We should end up with 92. We can write that as an equation, right? if we start at 52 and then add 8 Ds, we should end up at 92. Hey, that gives us an equation to solve for D. So then this is just simple algebra, right? Subtract the 52 and D equals 5. So lo and behold, we figured out what 5 is. We figured out what the common difference is. Now we could then do the same logic to figure out what the first term is, but let's go to the original instructions. It didn't ask us to find the nth term, so I'm not going to bother with finding what the first term is. If the question said find the nth term, then I'll go ahead and figure out what a sub 1 is, because you sort of need it. But no, let's just go ahead and answer the question directly. Let's find the 1000th term, and we're going to use the same logic here. So we have two starting places. It doesn't matter where we start with. I'm going to start with the closest numbers, and so the 19th term is closer to the 1000th term. So the logic is we're at the 19th number, and I want to go to the 1000th number. I know that the 19th number is 92, and the question is, how many D's are there between the 1000th number and the 19th number, right? So it's 1000 minus 19, which is what, 900 and what is that? 80. Why can't I do basic math now? 981 D's. So I know that there are 981 D's that are separating between the 19th term and the 1000th term, and I'm going to grab a calculator right now because I can't do that in my head. So what is our logic? What is our idea? If I start at 92 and I add 981 D's, but we know what D's are, right? D's are 5. That should give us the 1000th term. Hey, that's exactly what the question's asking us. So if I pop this guy into my calculator, I get 4,997 as the 1000th term. Just for fun, even though it didn't ask for it, let's just say it wanted the nth term. Let's say it wanted you to find the full formula. So I'll do this in a different color. This is sort of like a sidebar, extra stuff. Right? Find the nth term. Again, it's sort of funny. I don't really use the formula. It's all 100% logic. So you do the same concept. You start with any known value. I like to start with the one closest to the thing I'm solving for. So the 11th term is a lot closer to the first term. So, and it's the same logic here. So here's the first term. Here's the 11th term. I know that this is 55. Was it 55? 52. This is 52. And by simple mental math, I know there are 10 D's in between. So if I start the first term, which I don't know what it is, so it's a variable, and I add 10 D's to it, which I know was 5, I should end up with the 11th term, which is 52. Hey, this gives us an equation to solve for the first term, right? So I suppose the moral of the story is, yes, technically there is a formula to follow, but I really, when it comes to sequences, it's all patterns, it's all logic. You can certainly do everything logically. There you go. So the stuff in blue was sort of, a bonus question, an extra trivia thing. But yeah, arithmetic sequences, they are fun to do and easy to do because the idea is that they're not random patterns, they're not random sequences. They follow a logical progression. They're constantly adding or subtracting in the case of negatives, and because they're predictable, they should be easy to work with. And they are easy to work with. They're fun too. So, how about it? Good luck.